probability and statistics, counting, and combinatorics. Okay, now this is the second part. So let's check it out. And it is straightforward, not hard. And it helps us evaluating the probability in multiple cases. So let's delve into it. Let's start with the rule of product, which might be a review to something that you've already seen in the previous part or previous chapter. Rule of product. If you perform two tasks in sequence, the first task can be done in m ways, the second can be done in n ways. So the total number of possible outcomes is m multiplied by n. Here's what we're talking about, to give you an example. Let's say a license plate in the US has two letters, with each letter having possible values of A to Z. 26 possibilities. Why? Because you have 26 letters, 26 characters in the English alphabet, and you have 3 digits or 3 placements. Okay, each placement, each digit can have a value from 0 to 9, which is in total 10 values. How many possibilities do we get? Now, this is a permutation with repetition that we haven't gotten to yet, but we will get to. I can actually explain it right now, right off the shelf at this moment. So, you have, how many letters do you have? Or how many possibilities, I'm sorry. How many possible letters can you have? You have 26 possibilities for the alphabet in English language. Okay, on a license plate. So you have 26 possibilities. 26. And how many actual letters do you have on the plate? How many actual placement? You have 2 letters. So it is 26 to the power of 2. Multiplied, we multiply it by how many digits, possible values for a digit do you have? From 0 to 9, correct? So it is 10. Why? Because from 0 to 9, it's 10 possible digits. 0, 1, 2, 3, all the way to 9. And how many locations, how many placements for how many actual digits do you have on the plate? You have 3 digits. So to the power of 3. 26 squared times 10 cubed equal a total of 676,000 values or license plates that you can get. Now the rule of sum or addition rule. If you have 2 different methods to do something, like method 1 has A ways and method 2 has B ways, then the total possible outcomes in this case for A or B, and mind the language here, A or B is A plus B. Example, a bag contains 3 different balls of glass and 5 different balls of plastic. How many possibilities someone reaching to the bag would get among plastic and glass? Okay, how many possibilities? Let's say you have 3 different balls, different meaning, different colors, different features, whatever. But they are glass, and 5 different balls of different colors, you can assume, made of plastic. How many possible outcomes you would get if someone reaches to the ball, okay, to the box or whatever? How many possible draws you can get, possible options that you can get from the draw? You can get either the first, second, or third ball of glass, or the first, second, third, fourth, fifth of glass. Okay, or plastic, I'm sorry. So you have 3 glass, 5 plastics. The total of them is 8 choices, 8 different balls that you can get. This is how we add them, okay? And when you say the probability of getting a ball of glass or a ball of plastic, it is probability of getting a ball of glass is 3 divided by 8. The total is 8 plus, because why? Or getting a ball of plastic, 5 divided by 8, which is 8 divided by 8 or 100%. Clear? Hopefully it is straightforward. Okay, again, as a reminder, so the probability of an event is given by the number of favorable outcomes divided by the number of all possible outcomes, or the total of possible outcomes. Counting principles. Okay, so you have counting with repetition. Let's say you have a PIN code for an ATM access, and it's supposed to be 4 digits. Each digit can have 10 possible outcomes from 0 to 9. How many possible pins you can get? Now you can pause the video, turn your head sideways and try to figure this out. Okay, but the thing that we need to take, pay attention to is the fact that here we have a permutation with repetition, meaning that you can get 4 zeros within the pin code. Usually no one has 4 zeros, but you get my point, okay? Like you can get a pin code of 1134. So 1 is repeated twice. There's no problem. You have the repetition factor. So what would be the formula to get the total number of outcomes for that pin code? How many? What's the maximum number of pin codes that you can generate for this ATM machine to give them to your clients? This is the formula, and we've seen it a moment ago, okay? Because the license plate was with repetition, an example with repetition. Okay, so you have, let n be the number of different values each digit can have. In this case, you have 10 possible values, okay? R is the number of placements or digits, which is 4 possible pins, 4 possible numbers within the pin, okay? Then the total number of sequences that you can generate is given by total number of possible values, which is from 0 to 9, or 10 values, okay? 0, 1, 2, 3, 4, all the way to 9. These are 10 values. How many placements you have? How many digits within the pin code that you have? It's 4 placements. So it is 10 to the power of 4, or 10,000 possible values. Permutations or ordered arrangements. Here, without repetition, meaning that the number cannot reoccur, okay, within 2 placements, the same. So when you have a sequence like 0015, okay, it's not allowed. Why? Because 0 cannot occur twice. So you have the same elements, like when we say how in how many ways you can arrange 5 colored balls. Okay, each colored ball would be placed once. Okay, it cannot occur twice. It cannot exist at the same time on 2 positions. It's either left or right. Okay, but you can arrange it differently each time, meaning that it can be placed on the left at the first time and the second time on the right. Okay, so you're changing arrangement. All right, now in this case, the permutation of nr, this is how we write it, is given by n factorial divided by n minus r factorial. R is the number of placements and n is the different possibilities. Okay, so as an example, how many ways can we assign 3 medals, gold, silver, and bronze, among 6 athletes? In this case, you have probability of 6 to 3 is equal to n factorial. So we have 6 different athletes divided by n minus 3. So 6 minus 3 different medals, okay, which is 3 factorial, equal to, by the way, this is how we can also evaluate it. 6 factorial is actually 6 times 5 times 4 times 3 factorial, okay? So you can factor out the 3 factorial from the numerator and the denominator, and you get 6 times 5 times 4, which is 120. Combinations, here, no repetition should take place, but also on top of that, the order doesn't matter, okay? So this is what the combination means. It is a combination, like a mixing without repetition of numbers, of values, and the order doesn't matter, meaning that you have, let's say you placed, okay, 1 3 4 5, correct, or 1 5 4 3. We flipped the order. This should be counted once, not twice. That's the difference. This is given by n factorial divided by r factorial multiplied by n minus r factorial. Example, how many ways can we choose 3 cards out of 52? Okay, now if you chose ace and spade, 5 spade, like ace spade, 5 spade, 3 spade, let's say, or 3 spade, 5 spade, ace spade, like in a reverse order, this should be counted once. Okay, it doesn't matter, like the first one is not different than the second one. The order doesn't matter in this case. So how many possibilities you would get? It's given by how many cards do you have within a deck? You have 52 cards, 52 possible cards. So it is n factorial, which is 52 factorial, divided by how many cards are we drawing? 3 cards. Okay, so 3 factorial divided by 3 factorial multiplied by 52 minus 3 factorial. It is 22,100 possible combinations. Now, to give you another example which makes it simpler. Okay, let's say you have 3 people. One is Spanish, let's say. The other is American. The other is Italian, SAI, okay? And we want to know in how many ways you can seat them over 2 chairs, okay? So you have 2 chairs and 3 people from different nationalities, so that you would distinguish them easily, okay? How many ways and how many ways they can be seated on the chairs? It is given by permutation of NR. Definitely there's no repetition in this case because each one of them can be seated once. You cannot duplicate it and move him over another seat while he's still seated on the first one. He cannot be seated twice. However, each order is 1 count. So there are no repetitions, but you have different arrangements that count. So P and R is equal again to n factorial divided by n minus r factorial, given by n is the number of people that want to be seated. So 3 types of people, factorial, divided by n minus r, this is n, different possibilities of people, and this is r, which is the placement of seats. So it is divided by n minus r factorial, or 3 minus 2 factorial, which is 1 factorial, or 1. This leaves us with 3 factorial equal to 3 times 2 times 1, or 6. Let us check it out. You have 2 seats. Let's start with S and A. So you can seat them S, A, Spanish, American from left to right, or American, Spanish. Then you have S and I, Spanish, Italian, or Italian, Spanish. You have A and I, so American, Italian, American to the left, Italian to the right, and Italian to the left, American to the right. And that's it. How many arrangements do we have? 1, 2, 3, 4, 5, 6. So this value here is absolutely correct. You have 3 by 3, or total of 6 ways to arrange these 3 people over 2 chairs. Combinatorial identities, so you have like symmetry identity, nk, okay, combination between nk is equal to n minus k, gives us the same result. So choosing k items to include same as choosing n minus k to exclude. Okay. Pascal's identity, so nk, combination of nk can be rewritten as n minus 1k plus n minus 1 k minus 1. Okay, this as the combination of these 2 groups. So the k subset either includes a specific distinguished element or doesn't. Vandermonde's identity, so combination of m plus n r is equal to sigma k equals 0 to r of mk, combination of mk, multiplied by n, the combination of n of r minus k, or whatever r value is. Okay, these are formulas. I know that they can get crazy. Okay, at times they are beneficial. You don't have to memorize them, or some of them perhaps. Like the sum of all combinations, sigma from k equals 0 to n. Okay, what this means is the combination between, let's say, 5 and 1, 5 and 4, 5 and 1, 5 and 2, 5 and 3, 5 and 4, 5 and 5, all of the combinations from 0 to up to 5 is given by 2 to the power of n, which is, let's say you have 5, so that would be 32 combinations. Okay, so in other words, this can be written as, let's say, n equal 5 as an example. It would be the combination from 0 to 5 plus combination from 1 to 5 plus combination from 2 to 5 all the way to 5 to 5. Okay, binomial theorem identity, a plus b to the power of n. Okay, and we will explain the binomial later, is given by sigma k equals 0 to n, combination of nk multiplied by a to the power of n minus k times b to the power of k. Okay, we'll leave this to later. So combination permutation relationship, there's a relationship between combination and permutation. Actually, the permutation is given by the combination of n and k multiplied by k factorial. Also, hockey stick identity, so let's say sigma I equal k to n, and we're combining I and k. I starting from k all the way to n. So it is I that's scaling up, k remains the same. This is given by, or it can be re-evaluated using another formula, which is n plus 1 divided by k plus 1. So this sum gives us this value. Probability with counting. Let's say you have a population of size n. Now here is where Bernoulli equation takes place. So you have a population of size n containing k successes. So k number of values are success to us if you draw either this one among the k set. Okay, and n minus k is all the failures, which is everything but the k, everything with the n set, within the n set, except the k outcomes. We draw a sample of size n without replacement. The probability of getting exactly k successes in the sample is given by, and this is very important, you need to memorize it, p of x equal k is equal to combination of between k, all the successes, and k, the required number of successes, multiplied by n, capital N minus capital K, and lowercase n minus lowercase k, you see, divided by capital N, which is all the values in the sets, combination between n, which is the entire set, and lowercase n, which is the numbers that we are drawing. Okay, we are drawing 3 balls out of 10. 10 would be capital N, 3 would be lowercase n. As an example, try to think about it. Let's say you want to draw n equal 5 cards from a standard deck. A standard deck contains 52 cards, correct? Now, there are k aces, 4 aces, okay? So capital K is 4 possible successes. What is the probability of exactly getting 2 aces? 2 aces, not 4. So all possibilities within the deck are 52 cards. That's capital N. We are drawing out of these cards only 5 cards. That's lowercase n. Within these 5 cards, we are trying to assess how many, like what's the probability of getting 2 aces among these 5 cards, given that the possible successes within the entire deck is 4 aces. Within the entire deck, you only have 4 successes. 4 aces, you know, that would be a successful outcome. Yeah, if you want, think about it for a moment and get back to the solution. Okay, coming back. So, again, the probability of x equal 2, x equal k, or x equal 2 is given by capital K, lowercase k, meaning the total number of successes, which is 4, combined with the exact number of successes required, which is 2, multiplied by capital N minus capital K, which is 52 cards minus 4 aces, and lowercase n minus lowercase k, so 5 cards minus k, which is 2 aces that are required in the draw, divided by capital case n, 52 cards, and, you know, combination between 52 cards, capital case n, and lowercase n, which is the 5 cards that we're talking about. It gives us around 4% probability. Now, again, as a reminder, okay, going back to the formula, like the combination of 4, 2 is given by n factorial, not this n, not this 5. For I'm talking about this case here alone. So combination of 4, 2 is n factorial divided by r factorial times n minus r factorial. This is given by n factorial here is 4 divided by r factorial, which is 2 factorial, multiplied by 4 minus 2 factorial, which is 2 factorial, correct? So it is, yeah, 4 factorial is, one moment, four factorial is simply 4 times 3 times 2 factorial divided by 2 factorial times 2 factorial. 2 factorial, actually 2 factorial is 2, but here we've eliminated these two values. 4 divided by 2 factorial, which is 2, multiplied by 3 equal 6. Okay, so that is the value for the first one here, and of course you can apply the same formula to get the other ones. You'd end up with a probability of 4%, as we mentioned.